you remember in this definition, in this kind of deformation profile, you remember that because of the curvature, internal moment is what? Because internal moment is this M. This is the internal moment that we're looking at here. M internal moment equals negative of EI times Y double prime, right? So the whole thing eventually can be written as what? That can be written as negative. Well, if the first term is associated with a negative sign and the second term is also associated with a negative sign, shall we just cancel them? Right? We can cancel it because you have the negative sign here, this negative sign, and the first one also has a negative sign. We can just cancel it out. I'm going to write the positive sign version, and that means that becomes EI times the fourth order derivative. So we can write it like this. Plus P times the second order derivative to be 0. So this is the fourth order differential equation approach, the governing equation. For exactly the same column, which is what we call Euler's column. They're both governing equations. Now, what is the general solution? Or the complete solution for this column and for this governing equation is something like this. Of course, we need to know the value of these coefficients, but y of x equals a times the sine kx plus b times cosine kx plus c times x plus d. This is the general solution, which is the complete solution of y of x. Now you notice that in order to fully evaluate this variable y, you will need 4 boundary conditions to solve for these 4 coefficients a, b, c, d.
And k remains square root of p over ei?
Precisely. Now, let's compare these two approaches. This is 37. What would you choose? Second order or the fourth order? Well, second order is good because what? Because second order DE. It requires less boundary conditions, basically only 2, because you only have 2 variables or 2 coefficients. That means you only need 2 boundary conditions to solve for it, and that of course represents the mathematical convenience in this kind of problem solving. Fourth order. Of course, more BCs. So it's not preferred. However, the power of the fourth order differential equation is that instead of taking the free body diagram of a section including the boundary condition, the fourth order differential equation is true throughout the entire structure. Second order, you need to know the boundary condition. In this case, it may be obvious. And some of you may wonder, the professor, what will be the case that we don't know the boundary condition? Well, you know what? For real structures, when you want to analyze the buckling potential of real structures, you look at the steel bridge, and the steel bridge has been, I don't know, 70, 50, or even 80 years old. It was designed to have a hinge, but after so many years in service, the hinge support was corroded, or the roller support was corroded. Can you still argue that the roller support is still roller? Can you still say that? Probably not, right? If you go to visit the bridge, you look at it, you say that, well, I think this part is roller, but when you look at it, the forcing is corroded. You probably will not say that roller support, as it was designed, you will not consider that still a roller. You will consider that as a roller with some sort of frictional resistance, correct? That's the problem with the second order differential equation. You need to know precisely what's going on with your boundary conditions. If you don't know that, fourth order differential equation is the most powerful. Reason number one, even though mathematically it's more convenient for us to use the second order differential equation approach, but knowledge about BCs is required. And for the fourth order differential equation, it's not required. No need to know BCs. Even from what? Even from your formulation. And there's a huge difference. Because from the very beginning, in the second order approach, you actually have to know what are the actions at the support, right? If you don't know it, you cannot even arrive at the governing equation. In this case, the boundary condition is basically affecting this end. You have to know that. Otherwise, you cannot formulate it. But in the fourth order differential equation approach, we did not consider boundary. Everything is inside the structure. And that's why the fourth order differential equation, you may consider is your ultimate weapon. If you don't know the boundaries condition for sure, start with the fourth order differential. Yes, it may look a little bit tedious, but remember we've been using displacement boundary condition. We also been using slope, right? The derivative boundary condition. So it's not that difficult to get as many boundary conditions as possible. Plus, today we even talk about the use of continuity condition. So finding enough numbers of boundary conditions for the fourth order differential equation approach is not a big deal. However, for this structural stability, you notice that we make assumptions and we just carry away with our assumptions. So when it comes to exams or the quizzes, please don't get me wrong. I'm telling you that the fourth order differential equation is the most powerful one, but I'm not suggesting to use the fourth order differential equation on the exams, because the practical problems we talked about before, they don't happen on the exams. So you will probably not, let's put it this way, it may be unwise to use the fourth order differential equation on the exams because that takes you longer time to formulate it and to solve it. Also, it is theoretically the most powerful weapon to find the buckling load. And is that clear? Good. Okay, so this is how we compare these two. And for other structures, I may use the fourth order differential equation, perhaps on one or two examples in this class. Otherwise, we will stick to just the second order differential equation approach because it's easier and it's faster. Okay. All right. And there's one more thing I'd like to talk about before I let you go. And this concept is what I call material strength limit. You remember we talked about this graph. And I think that it was Fatlum, and he asked me the question about what's the point when these two intersect? And this is the curve that I think, right? which we have seen it before. The y-axis is the stress, sigma, and the axis is the ratio between the length of the column divided by radius of gyration, which is r. And this ratio, by the way, is what we call slenderness ratio. So I show you that there is a curve which goes something like this. This curve, in fact, is predicted. It was actually not experimentally determined. Experimentally, we're going to determine different values for the data points. But in theory, this curve was actually calculated. So how do we calculate this? And I'm going to show you how we actually calculate this one here. And first of all, we know that PCR or PE equals pi squared EI over L squared, right? That we know. And for simply supported columns, this PE, which is constant, happens to be the critical load for simply supported columns subjected to an axial force that we know already. You have seen that already. Now, we can also write this by what? By finding the critical stress. So if you have a critical load, what is the critical stress? How do you find critical stress in here? Suppose you have a column, right? Which is this column right here. You have the critical load provided. How do you calculate critical stress? Is the force, is the force divided by the cross-sectional area, right? So this is very straightforward. You just divide PCR by A, capital A. Then you can find the critical stress, sigma CR. Now, how does it look like? If you have the expression of that, and you just divide everything, and that's actually will give you this expression. That is pi squared times E over I over A over L squared, right? This is the expression of sigma CR, correct? Now, you also remember last time we said that we define this radius of gyration to be what? Radius of gyration is actually I over A equal to the square root of I, mass moment of inertia, divided by cross-sectional area. And this is the same thing like we did before, where you want to say this R equals the square root of I over A. Either way is fine. Now, with this, you can actually move this ratio, right? The I over A, replace I over A with what? With R squared, and then this can be written as pi squared E over L over R squared. I'm sorry, there's the whole thing is out. So let's rewrite it like this. Correct? Is that clear?